Hi friends, welcome to Aspirants, the vision to reality, the knowledge platform. Enjoy the session. Stay tuned with us to be an aspirant. Hello everyone. From this video onwards, we are starting the first chapter of Class 11 Chemistry. The name of first chapter is Some Basic Concepts of Chemistry. This chapter deals with the simple concepts, the fundamental concepts, terms, calculating procedures, units and conversions, all such things in chemistry. And this chapter is divided into 3 parts. Now you are watching the first part of this chapter. Keep watching. As I have mentioned earlier, this chapter is divided into 3 parts, and the following topics will be discussed in this video. They are: number 1, the importance of chemistry; number 2, the nature of matter; number 3, the properties of matter and their measurement; and number 4, uncertainty in measurement. Number 1, the importance of chemistry. Science can be classified into major disciplines such as physics, chemistry, biology, geology, etc. So, here we are focusing only about chemistry. What do you mean by chemistry? Chemistry deals with the composition, structure, and properties of matter. In other words, we can say that chemistry is a branch of science that studies the composition, properties, and interaction of matter. Now, what do you mean by matter? Anything that has mass and occupies space is called matter. We will discuss about matter in this video later. Now, chemistry is intertwined with other branches of sciences like physics, geology, biology, etc. That means chemistry plays an important role in every aspect of science. It also plays an important role in daily life, and it has numerous applications in many areas. Now we are moving on to the applications of chemistry. Chemistry plays an important role in the manufacture and synthesis of a large variety of chemicals. Some of them are mentioned here: fertilizers, which are used for plant growth; alkalis, which are extracted from leaves; then acids, found present in the fruits. Both of them maintain the pH of the human body. Then salts. Salts are the products obtained by the neutralization of acid with a base. The given picture contains a large variety of salts. You will study more about salts in coming chapters. The food we eat, the clothes and accessories we wear, all of these contain colors. So dyes are the chemicals which are used for color. Then drugs. Drugs are chemicals which produce a biological response. When the biological response is therapeutic and useful, these chemicals are called medicines and are used in diagnosis, prevention, and treatment of diseases. If taken in doses higher than those recommended, most of the drugs used as medicines are potential poisons. Soaps and detergents are chemicals that are used for cleaning purposes. Hair conditioners, shampoos, toothpaste, laundry detergents, etc. comprises of soaps and detergents. The chemical structure of soap molecule and detergent molecule will be discussed in coming chapters. Chemistry plays an important role in meeting human needs for food, healthcare products, and other materials aimed at improving the quality of life. Many life-saving drugs such as cisplatin, Taxol are effective in cancer therapy. The structure of cisplatin can be seen here. It consists of a central platinum atom surrounded by 2 chlorine atoms and 2 ammonia molecules. The terms atoms and molecules will be discussed later in this video. The structure of Taxol is given here. We can see 3 aromatic benzene rings in the molecule of Taxol. I hope you have watched our previous video about the structure of benzene, so there's no need to discuss in detail about that. So cisplatin and Taxol are the drugs used for cancer treatment. Then the third one is azidothymidine, which is used for helping AIDS victims, and they have been isolated from plant and animal sources or prepared by synthetic methods. The production of superconducting ceramics, conducting polymers, optical fibers, and large-scale miniaturization of solid-state devices are also included in the application of chemistry. Superconducting ceramics have infinite conductance and zero resistance. Certain polymers have the ability to conduct electricity. They are shown in this picture. The cables that we are used for telecommunication and internet are optical fibers. Safer alternatives to environmentally hazardous refrigerants like chlorofluorocarbons, responsible for ozone depletion in the stratosphere. Now, what do you mean by chlorofluorocarbons? They are molecules consisting of carbon atoms, chlorine atoms, and fluorine atoms. They are emitted by air conditioners, refrigerators, etc. The uncontrollable emission of these chemicals responsible for ozone depletion in the stratosphere. Then enzymes. Enzymes are biological catalysts. They are essential for our metabolism. We will study about enzymes in detail in coming chapters. Number 2. Nature of matter. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. Some examples can be seen in this picture, like skateboard, pencil, milk, drink, wind, air, fog. All of these has a specific mass and they occupy some space. So they are all examples of matter. Now, at present, there are 7 states of matter have been discussed and discovered by scientists. On this moment, we are only dealing with 3 major states of matter. They are solid, liquid, and gas. The examples of solids are hat, pencil, table, bicycles, etc. The examples of liquids are milk, soft drinks, soup, rain, juice, etc. Examples of gases are air, oxygen, hydrogen, nitrogen, etc. Now we are comparing solids and liquids and gases. For solids, they are rigid, they have fixed shape, and they have fixed volume. The particles are not free to move. They are about only to vibrate from their mean position. While dealing with liquids, they are not rigid. They have no fixed shape, but they have fixed volume. The particles are about to move within the surface of the liquid, and they take the shape of the container in which they are kept. They have no fixed shape. Third one is gas. They are not rigid. They have no fixed shape. They have no fixed volume. The particles are free to move. We are dealing with three states of matter and their properties: solid, liquid, and gas. Now we are going to discuss about phase transformation. What do you mean by phase transformation? It is the transition of physical state from one form to another. Examples of phase transformation is melting of solid, freezing of liquid, condensation of gas, vaporization of liquid, etc. When a solid melts, it becomes a liquid. When a liquid vaporizes, it turns into gas. Similarly, when a gas condenses, it turns into liquid, and liquid undergoes freezing to give a solid. In addition to that, there are two more terms: sublimation and reverse sublimation. Now, sublimation refers to the direct phase transformation from solid state to gaseous state. In such cases, the substance do not exist in liquid form. Examples of sublimating solids are camphor, naphthalene, iodine solid, etc. The reverse of the process is known as reverse sublimation. At the macroscopic or bulk level, matter can be classified as mixtures or pure substances. Given below is a flow chart showing the classification of matter. Matter at first classified into mixtures, secondly pure substances. Each of them undergoes again classification: mixture turned into homogeneous mixtures and heterogeneous mixtures, pure substances turned into elements and compounds. We have discussed about matter. Anything which has mass and occupies space is called matter. And the remaining 6 terms are yet to be discussed. In the coming session, we will going to discuss about all of these 6 terms. The first one is mixtures. A mixture contains 2 or more substances present in it in any ratio, which are called its components. Examples of mixtures are air, tea, etc. Now, air is a mixture of various gases. We have learned from our childhood. So in air, the components present are oxygen, hydrogen, carbon dioxide, helium, etc. Second example is tea. In tea, the components present are sugar, water, milk, tea powder, etc. Now we are going to discuss about the 2 classification of mixtures: homogeneous as well as heterogeneous mixtures. In a homogeneous mixture, the components completely mix with each other and its composition is uniformly throughout. Which means in homogeneous mixtures, the concentration of each component remains the same in each and every single corner throughout the mixture. Example of homogeneous mixtures are sugar solution in water, salt solution in water, etc. The second classification is heterogeneous mixtures. In a heterogeneous mixture, the composition is not uniform throughout, and sometimes the different components can be observed. Example of heterogeneous mixtures are the mixture of salt and sugar, grains and pulses along with some dirt, etc. In heterogeneous mixture, the particles are not uniform throughout. That means the concentration of each component varies throughout the mixture. They are not evenly, or they are not uniformly equally distributed. Next one is about pure substances. They have characteristics different from the mixtures. They have fixed composition, whereas mixtures may contain the components in any ratio and their composition is variable. Now, pure substances have a fixed composition. Examples of pure substances are silver, copper, gold, water, oxygen, etc. Next one, the classification of pure substances. This is very, very important. Pure substances are classified into two. They are elements and compounds. What are elements? An element consists of only one type of particles. They may be atoms or molecules. Now, what are compounds? When two or more atoms of different elements combine, the molecule of a compound is obtained. Here, you can observe two additional terms, atoms and molecules. You will study briefly about atom in next chapter, namely structure of atom. Now I'm going to deal with atom. What is an atom? An atom is a fundamental particle of an element which shows the physical and chemical properties. Atoms can further be divided, but the further division of atom cannot possess the true identity or the true physical and chemical properties of a particular substance. So the basic fundamental particle of a substance which shows the physical and chemical properties are atoms. Now, what is a molecule? Two or more atoms combine together to form a molecule. Here are the examples of atoms: hydrogen, oxygen, nitrogen, copper, sodium. Examples of molecules mentioned here: a hydrogen molecule, an oxygen molecule. In hydrogen molecules, two hydrogen atoms combine together to form a hydrogen molecule. And the hydrogen molecule is a pure substance, but it is not atom, it's a molecule. Again, two atoms of oxygen combine together to form a molecule of oxygen. Oxygen molecule is a pure substance. It is not atom, it is molecule, but it consists of two oxygen atoms and is a pure substance. The given picture shows the difference between element and compound. The first row shows three elements. First one, nitrogen. Second one, oxygen. Third one, chlorine. So first case, the nitrogen element contains a diatomic molecule of nitrogen. Even though it contains two nitrogen atoms, it is a molecule and it is a pure substance. It is an element. Second case, oxygen molecule consists of two atoms, so it's a diatomic molecule of oxygen, and oxygen is a pure element. Third one is chlorine. The chlorine molecule consists of two chlorine atoms, so it is a diatomic molecule of chlorine. It is an example of element. The second row consists of compounds: water, methane, and ammonia. In water molecule, 2 hydrogen atoms and 1 oxygen atom combine to form a water molecule. We have discussed previously that atoms of different elements combine to form molecule of compounds. So here we can see in each compound there are different kinds of atoms. In water molecule there are 2 hydrogen atoms and 1 oxygen atom. Second case is methane. In methane there you can see 4 hydrogen atoms in a carbon atom. Third case is ammonia. In ammonia molecule 3 hydrogen atoms present in 1 nitrogen atom. That's the structure of ammonia. All these are examples of compounds and they are pure substances. The major classification of pure substances are elements and compounds. The elements and compounds are illustrated here as examples. Number 3. Properties of matter and their measurement. We have seen the definition of matter. Anything that has mass and occupies space is called matter. Then classification of matter: pure substance and mixtures, elements, compounds, homogeneous as well as heterogeneous mixtures. Now third one is the properties of matter and their measurement. Now every substance has unique or characteristic properties. These properties can be classified into 2 categories: physical properties and chemical properties. First one, physical properties. Physical properties are those properties which can be measured or observed without changing the identity or the composition of the substance. Some examples of physical properties are color, odor, melting point, boiling point, density, etc. Second one, chemical properties. The chemical properties can be measured or observed with changing the identity or the composition of the substance. The examples of chemical properties are acidity, basicity, combustibility, etc. Next, we are moving on to the measurement of matter. How the properties can be measured. Keep watching. We have been dealing with the properties and measurement of matter. Now, in order to measure any quantity or measurement of matter, we need certain dimensions or units, and we know that many properties of matter such as length, area, volume, etc. are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units, and we know that, for example, 6 centimeter, 7 feet, 5 kilogram, etc. So 2 different systems of measurement. They are the English system and the metric system were being used in different parts of the world. In the English system, the unit of weight is pound, and in metric system the unit of weight is kilogram. So we need a standard system. In other words, the need of a common standard system was being felt by the scientific community. The international system of units came into existence. As a result, it was established by the 11th General Conference on Weights and Measures. The SI system has 7 base units. These units pertain to the 7 fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc. can be derived from these quantities. So it is evident that there are 7 base units, and the other physical units can be derived from these 7 units, and we are going to see Which are the 7 base units? Finally, the 7 base units of SI system are meter, kilogram, second, ampere, Kelvin, mole, candela. Number 1. Meter. It is represented as a small letter m, and the quantity measured is length. Number 2. Kilogram. The unit symbol of kilogram is small letters K and G, and the quantity measured is mass. The SI unit of mass is kilogram. Third one, second. Second is measured for time, and the unit symbol of second is a small letter of S. Fourth one is ampere. Ampere is measured as a quantity of electric current, and the unit symbol is capital letter A. Number 5, Kelvin. The unit symbol of Kelvin is capital letter K, and Kelvin is a unit of temperature. Number 6, mole. The unit symbol of mole is small letter M-O-L. Mole is the unit of the amount of substance. Number 7, candela. Candela is the unit of luminous intensity. The unit symbol of candela is small letters C, D. Even though we have got the base quantity and base unit, we need a clear definition for each base unit. And the fact is, the definition must be a constant. That means it cannot be changed. So given here are the standard definitions for each base units. Number 1, the base unit of time is second, and the definition of second is 1 second is the duration of 919 crores 26 lakhs 31,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Second one, the definition of meter. 1 meter is the length of the path traveled by light in vacuum during a time interval of 1 divided by 29 crore 97 lakhs 92,458 of a second. Third one, the definition of kilogram. 1 kilogram is the unit of mass. It is equal to the mass of the international prototype of the kilogram. Now, what do you mean by the mass of international prototype of the kilogram? Which means the mass of 1 kilogram is taken as a mass of platinum iridium alloy, which is kept as a standard mass. That is the international prototype of the kilogram. Now, number 4 is ampere. The definition of ampere is, the ampere is that constant current which, if maintained in 2 straight parallel conductors of infinite length of negligible circular cross-section and placed 1 meter apart in vacuum, would produce between these conductors a force equal to 2 into 10 raised to minus 7 Newton per meter of length. Number 5, the definition of Kelvin. That means the definition of unit of temperature. Kelvin, the unit of temperature, is the fraction 1 by 273.16 of the thermodynamic temperature of the triple point of water. What do you mean by triple point of water? It is a temperature at which water can be found in three states: solid, liquid, and gas. Number 6, the definition of mole, that means the definition for the amount of substance. 1 mole is the amount of substance of a system which contains as many elementary entities as there are atoms in 0.012 kilogram of carbon-12. The elementary entities must be specified and may be atoms, molecules, ions, electrons, other particles, or specified groups of such particles. So basically, mole refers to the number of particles. Irrespective of their nature, they may be atoms, molecules, ions, electrons, protons, nucleus, etc. Seventh one is candela. The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 into 10 raised to 12 Hz, and that has a radiant intensity in that direction of 1 by 683 watt per steradian. Steradian is the unit of solid angle. So these are the definitions of base units. The SI unit of length is meter, but we have to measure length which is smaller than 1 meter as well as greater than 1 meter. In such cases, we need to add some prefixes along with the SI units to give another unit. The factor 10 raised to 1. The name of that factor is deca, denoted as dA. So 1 decameter equals 10 raised to 1 into 1 meter. 10 raised to 2 gives hecto. So 1 hectometer is equal to 10 raised to 2 into 1 meter. 1 kilometer is equal to 10 raised to 3 into 1 meter. Similar as follows: mega equals 10 raised to 6, giga 10 raised to 9, tera 10 raised to 12, peta 10 raised to 15, exa 10 raised to 18, zeta 10 raised to 21, iota 10 raised to 24. The factor 10 raised to minus 1 is denoted by the name deci, denoted by small letter d. Similarly, the factor 10 raised to minus 2 becomes centi. So 1 centimeter is equal to 10 raised to minus 2 into 1 meter. Then milli 10 raised to minus 3. So 1 millimeter is equal to 10 raised to minus 3 into 1 meter. Followed by micro, which is denoted by the Greek letter mu, gives the value of 10 raised to minus 6. Followed by nano, 10 raised to minus 9. Then pico, 10 raised to minus 12. Usually the distance between atoms are measured in terms of picometer, that means 10 raised to minus 12 into 1 meter. The factor 10 raised to minus 15 is known as femto, which is denoted by the symbol small letter f. The factor 10 raised to minus 18 is known as atto, denoted by the symbol small letter a. Followed by zepto, having a value 10 raised to minus 21. Then last octo, which gives a value 10 raised to minus 24. Next one, mass and weight. What is the basic difference between these two terms, mass and weight? Mass of a substance is the amount of matter present in it. We have learned earlier that anything that has mass and occupies space is known as matter. So, mass of a substance is the amount of matter present in it. Next one, weight. Weight is the force exerted by gravity on an object. Weight is the force exerted by gravity on an object. From these two definitions, it is clear that mass of a substance remains the same, whereas weight of a substance changes with the change in gravitational force of the Earth or any other celestial bodies. For example, if the weight of an object at Earth and the Moon are different, but the mass of the substance remains the same, because even if in Earth or in Moon, the amount of matter present in an object doesn't change, but the gravitational force exerted by the Earth and the gravitational force exerted by the Moon on an object changes. So, mass of an object is a constant and weight can be changed. In chemistry laboratory, how can we measure the weight of a suitable chemical? Here we use an apparatus as shown in the figure. It is known as analytical balance. It is shown in this figure and it is labeled. It consists of hooks, bow pointer, scale, pan, knife edge, beam, stirrup, balancing screw nuts, pillar, plumb line, and leveling screw. The leveling screw is used to make the object stable. That means to make the analytical balance horizontal with the surface. Volume. Volume is the quantity of three-dimensional space enclosed by a closed surface. It has the units of length, the whole raised to 3. That means a length cube. So, in International System of Units, also known as in SI system, volume has the units of meter cube. That means length into length into length. SI unit of length is meter, so meter into meter into meter gives meter cube. But again, in chemistry laboratories, smaller volumes are used. As we have discussed earlier, we add some kind of prefixes along with the SI units to convert it into desirable smaller units. Hence, volume is often denoted in centimeter cube or decimeter cube units. Then, a common unit, liter, denoted by the capital letter L, which is not an SI unit, is used for measurement of volume of liquids. We are much familiar with the unit liter and milliliter. So milli is 10 raised to minus 3, which is added to liter, which gives milliliter, 10 raised to minus 3 into 1 liter. So here's the conversion. 1 liter, which is equal to 1000 milliliter, and 1000 centimeter cube is equal to 1 decimeter cube. Now, let us see some of the measuring devices used in chemistry laboratories. Now, in chemistry laboratories, there are numerous devices used to measure volume. Now, we have to get familiar with some of the measuring devices which is used in chemistry laboratories. Keep that in mind about these apparatus. Let's watch. First one, pipette. A pipette is a measuring device which is used to take out solutions having volume ranges from usually 5 milliliter to 20 milliliter. The solution is filled inside the pipette is by sucking the air from the top opening and holding that opening using our index finger. Next one is burette. A burette is a measuring device which is usually we are taking for titration, volumetric analysis, volumetry, potentiometry, such kind of volumetric analysis. In burette, solutions having a volume range of 50 milliliter can be stored. We can see some graduation mark ranging from 0 to 50 can be found in burettes. So at the top the marking must be 0, at the bottom it stops to 50. There are some other kind of burettes too. In such burettes the maximum volume is 25 milliliter. So depending upon our convenience we are taking burettes up to our need. Then third one is graduated cylinder. A graduated cylinder, also known as measuring flask, is used to take solutions of desirable volumes. Graduated cylinders are of different sizes ranging from 10 ml, 15 ml, 20 ml up to 50 ml. Number 4, volumetric flask. A volumetric flask is used to prepare solutions of desirable concentration. We can prepare solutions of desirable concentrations by calculating the weight of substance needed and the volume of water needed. By weighing the substance suitably and then mixing the substance with the volumetric flask, we can prepare solutions of desirable concentrations. Volumetric flasks are of volumes ranging from 100 ml, 200 ml, 250 ml, 500 ml and 1 liter. Fifth one is beaker. Beakers are of different sizes ranging from 1 ml, 5 ml, 10 ml, 80 ml, 100 ml, 200 ml, 150 ml up to 500 ml. We can change the size of beaker up to the desired that quantity of solution that we want. Density and temperature. So first one, density. Density of a substance is the amount of mass per unit volume. So equation of density gives mass divided by volume. So the SI units of density is kilogram per meter cube. How the unit of density is kilogram per meter cube? the amount of matter, that means mass, the unit of mass is kilogram, the unit of volume is meter cube. So dividing mass per volume, that means mass divided by volume, so kilogram divided by meter cube or kilogram per meter cube. And this unit is quite large, and a chemist often expresses density in gram per centimeter cube. So we know that a kilogram is a larger quantity and meter cube is also a larger quantity. So we are taking solutions, and the density of solutions can be calculated in terms of gram per centimeter cube. Next one, temperature. Temperature is the average kinetic energy possessed by a substance. In other words, we can say that temperature is the degree of hotness or coldness of a body. There are three common scales to measure temperature. They are degree Celsius, degree Fahrenheit, and Kelvin. But the SI unit of temperature is Kelvin. Here K is the SI unit. But in our daily life, we are using degree Celsius to measure the temperature of objects, and degree Fahrenheit, which is used for clinical purposes. And now, these three units are interrelated by the following equations. That means we can convert the quantities from one unit to other. And these three units are interrelated by the following equations as degree Fahrenheit equals 9 by 5 of degree Celsius plus 32. That means the relation between degree Celsius and degree Fahrenheit. Then the relation between Kelvin and degree Celsius is K is equal to degree Celsius plus 273.15. These two equations are necessary for solving numerical problems. So please note down these two equations. The given picture shows the corresponding readings of Fahrenheit, Celsius, as well as Kelvin scales. We know that the boiling point of water is 100 degrees Celsius. So in Fahrenheit scale, the boiling point of water is 212 degree Fahrenheit. In Kelvin scale, it is 373.15 Kelvin. Similarly, we can check out other readings too. Then the freezing point of water is 0 degrees Celsius, and we know that. Here we can see the other corresponding measures also. 0 degrees Celsius correspond to 32 degree Fahrenheit as well as 273.15 Kelvin. At the bottom of that scale, that means minus 273 degrees Celsius, that temperature is known as the absolute zero temperature. At that temperature, it is taken as 0 Kelvin, which corresponds to minus 460 degree Fahrenheit, and this temperature is known as absolute zero. Number 4. Uncertainty in measurement. Doing calculations is inevitable in the study of chemistry. Many a times in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. During calculations, we get random values with positive, negative, whole, decimal numbers, etc. In such situations, we need a general formula to represent the numerical values in a uniform manner. There are meaningful ways to handle the numbers conveniently and present the data realistically with certainty to the extent possible. While calculating measurement, we get usually values ranging from 0 to positive infinity and minus infinity, whole numbers, fractions, decimals, etc. All we need is to generalize all these numbers in a standard form. And let's find out how do we convert the whole numbers into a standard form, or how do we represent the numbers in a standard form. Let's find out. The scientific notation is used to represent numbers in a standard form. That means we can represent decimal numbers, very small numbers to greater numbers, in a uniform manner. The general formula for scientific notation is capital N into 10 raised to small n, where capital N is the numerical part and small letter n is the exponential part. Here we can see three examples. The first number is 6.022 into 10 raised to 23. Here we are converting the number into a simplest form. For minimizing the digits to write, we are simply writing 6.022 as a numerical part and counting the rest of decimal places, and from the right hand side of 6 point we can see there are total 23 decimal places. So we can represent the number as 6.022 into 10 raised to 23. And this number is a constant. It is known as Avogadro number. We will study about this number in coming videos. The second example is 232.508. There also we need to convert it into a numerical part and exponential part. So while converting two decimal places to the left, we get 2.32508, and we are shifting two values to the left, so 10 raised to 2. Third example, 0.00016. There we are shifting the decimal place up to 4 digits to the right of number, so we get 1.6 into 10 raised to minus 4. So this is about scientific notation. I hope you understood. We will discuss about the addition, subtraction, multiplication and division of numbers and representation of the results in scientific notation. Multiplication and division of scientific notations. First one, 5.6 into 10 raised to 5 into 6.9 into 10 raised to 8. Here we are separating the numerical part and separating the exponential part, and writing the like terms together, we get 5.6 into 6.9 into 10 raised to 5 into 10 raised to 8. So x raised to a into x raised to b, that means x raised to a plus b. So we get 10 raised to 5 plus 8. which is equal to 5.6 into 6.9 into 10 raised to 13. 5 plus 8, we get 13. Now simplifying the answer, we get 38.64 into 10 raised to 13. Next example, 9.8 into 10 raised to minus 2 into 2.5 into 10 raised to minus 6. Here also we are separating the numerical part and separating the exponential part. So here 9.8 into 2.5 into 10 raised to minus 2 plus minus 6. That means 10 raised to minus 2 into 10 raised to minus 6 equals 10 raised to minus 2 plus minus 6. Now multiplying the positive sign into inside the bracket, we get the negative sign. So it is equal to 9.8 into 2.5 into 10 raised to minus 2 minus 6, which is equal to 24.50 into 10 raised to minus 8. The numerical part 24.50 is obtained by multiplying the numbers 9.8 and 2.5. The exponential part minus 8 is obtained by simply adding the exponential terms minus 2 and minus 6. Third example is the example for division. 2.7 into 10 raised to minus 3 divided by 5.5 into 10 raised to 4. Here also we are separating the numerical part and separating the exponential part as well. So separating the numerical part, we can write as 2.7 divided by 5.5, and separating the exponential part 10 raised to minus 3 divided by 10 raised to 4, which is equal to 10 raised to minus 3 into 10 raised to minus 4. So again applying the identity, x raised to a into x raised to b is equal to x raised to a plus b. So here 10 raised to minus 3 minus 4, which is equal to 0.4909 into 10 raised to minus 7. Here the numerical part 0.4909 is obtained by dividing the numbers 2.7 by 5.5, and also the exponential part minus 7 is obtained by adding simply the exponential terms minus 3 and minus 4. Next one, addition and subtraction. So given here, question number 1 is an example for addition and number 2 is an example for subtraction. So let's find out. Number 1, 6.65 into 10 raised to 4 plus 8.95 into 10 raised to 3. While analyzing these two terms, it is clear that the exponential terms are different. So we need to equalize both the exponential terms as a single term. For that, we are taking the second term 8.95 into 10 raised to 3. We have to express that term in terms of 10 raised to 4. For that, we can rewrite as 0.895 into 10 raised to 4. How do we do that? There, one decimal place is changed to the left side. So, one more number must be added to the exponential part. So it becomes 0.895 into 10 raised to 4. Now adding these two terms and separating the numerical part and separating the exponential part. So 6.65 plus 0.895 into 10 raised to 4. Here 6.65 and 0.895 are multiplied with 10 raised to 4. So 10 raised to 4 is a common term. So we are taking common outside and we can rewrite it as 6.65 plus 0.895 of 10 raised to 4, which gives the answer 7.545 into 10 raised to 4. The numerical part 7.545 is obtained by simply adding the terms 6.65 and 0.895. The next example is subtraction of scientific notations. 2.5 into 10 raised to minus 2 minus 4.8 into 10 raised to minus 3. So again we can see that the exponential terms are different. While in the case of multiplication or division, we need simply to add the exponential terms, but while operating addition or subtraction, the exponential terms must be equal. For that, we are equalizing the exponential term, as we are converting the term 4.8 into 10 raised to minus 3 as 0.48 into 10 raised to minus 2. Similar is the case here as mentioned above. We are changing the decimal place one digit to the left. So we get 0.48 and we are adding 1 to the exponential part. So minus 3 plus 1, it gives minus 2. So rewriting it as, which is equal to 2.5 into 10 raised to minus 2 minus 0.48 into 10 raised to minus 2. So 10 raised to minus 2 is the common term for both 0.48 and 2.5. We can simply rewrite it as 2.5 minus 0.48 into 10 raised to minus 2, which is equal to 2.02 into 10 raised to minus 2. The term 2.02 is obtained by subtracting 0.48 from 2.5. Accuracy and precision. The term accuracy and precision are used while analyzing a set of values for a particular experiment. And these two terms are very important, and these two terms are very paradoxical. Now, what's the difference between the term precision and accuracy? Precision refers to the closeness of various measurements for the same quantity, which means if we get a set of values for a given experiment, and if those values are closely connected or closely related, closely focused towards a particular range of value, then we can say that the set of values are precise. But we do not know whether the focused value is a true value or not. Those values are only precise. Next concept is accuracy. Accuracy is the agreement of a particular value to the true value of the result. That means if we are conducting an experiment and we got a set of values, if the values we got are closely related to the true value or the exact theoretical value, that we can say that those values are accurate. Or in other words, if the values we obtained are closely related to the expected or true value, then we can say that those values are accurate. So given below is a picture. You can see a picture showing 4 variations or 4 combinations of accuracy and precision. Let's figure out each of them. Combination number 1. accurate and precise. There you can see some readings: 1.001 kilogram, 1.000 kilogram, 0.998 kilogram, and 1.003 kilogram. So these four values are closely related to 1 kilogram, right? So these four values are precise. Then while analyzing the picture, we can see that all the values or all the dots are focused on the center. That means the value we expected is the value we got here. So the combination is accurate and precise as well. Second case, combination number 2, accurate but imprecise. Let's figure out each values. 1.173, 1.284, 0.881, 0.917. We can see very clear that these values are much more far away from the previous case. So the values are not precise, or the values are imprecise, but the values are accurate. While taking the average of these values, we get roughly as a 1 kilogram. So the values are accurate, but they are not precise, imprecise. Also, it is mentioned in the diagram that the dots are focused very far away, which means they are imprecise. Third combination, inaccurate but precise. Let's find its values. 2.814 kilogram, 2.837 kilogram, 2.822 kilogram, 2.819 kilogram. So these four values are roughly related to 2.8 kilograms. So the values are very close to each other and they are precise, but they are not accurate. That means from the figure we can see that the dots are placed far away from the center and assembled far away from a particular point. So they are not focused at the center, so they are not accurate. They are inaccurate values, but they are very close. That means they are precise. The fourth combination is inaccurate and imprecise. Let's find out. 0.312 kilogram, 6.398 kilogram, 2.141 kilogram, and 0.805 kilogram. Here the four values are far away from each other, so they are imprecise, and also they are not focused at a particular center. They are not focused at the center of that figure, so they are inaccurate as well. I hope you understood the terms accuracy and precision through the values as well as the diagram. Significant figures. Every experimental measurement has some amount of uncertainty associated with it. The uncertainty in the experimental or the calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known to certainty. Now, when analyzing a particular value that we got from an experiment, we can predict the percentage of reliability as well as the percentage of non-reliability. That means to some extent we cannot fully trust a particular value. That means there has some sort of uncertainty in a particular value, and the degree of uncertainty can be measured by understanding some criteria of significant figures. So basically there are 4 rules for determining the number of significant figures. Rule number 1: all non-zero digits are significant. All non-zero digits are significant. For example, 285 centimeter. There is not any decimal points and there is no zeros either. So in 285 centimeter there are 3 significant figures. That means the 3 digits are non-zero digits. So all non-zero digits are significant. Second example, 0.25 ml. 0.25 ml. In 0.25 ml there are 2 significant figures, because after 0 and after 0 point there are 2 non-zero digits. So there are 2 significant figures. And from the number 0.25 we can understand that there may be some digits after 25. That means 0.2500, 0.2501, 0.2574, etc., etc. So those values are uncertain. So here are only 2 significant figures. The digits coming after 25 are uncertain. Rule number 2: zeros preceding the first non-zero digit are not significant. Such zero indicates the position of decimal point. For example, 0.03. In 0.03 it has only 1 significant figure. That means 0 preceding to first non-zero digit are not significant. In 0.03, 3 is the first non-zero digit. After 3 there may be some zeros. We don't know that. We don't know about that. So 3 is the first non-zero digit and there are 2 zeros preceding 3. So those 2 zeros are not significant. In short, in 0.03 there is only 1 significant figure, and that is 3. Second case, 0.0052. There 5 is the first non-zero digit and there are 3 zeros preceding the first non-zero digit 5. So those 3 zeros are non-significant. In short, in term 0.052 it has only 2 significant figures and they are 5 and 2. Rule number 3: zeros between 2 non-zero digits are significant. Zeros between 2 non-zero digits are significant. For example, 2.005. 2.005 has 4 significant figures, which means we have to add those 2 zeros along with the digits 2 and 5. Why is it so? Because the 2 zeros exist between 2 non-zero digits 2 and 5. So there are total 4 significant figures. In short, if a number has numerous zeros between 2 non-zero numbers, then while calculating the number of significant figures, we need to add the non-zero digits as well as the number of zeros. So total number of zeros here 2. Total number of significant figures 4. Rule number 4: zeros at the end or right of a number are significant provided they are on the right side of the decimal point. For example, 0.200 gram has 3 significant figures. It's something related I have mentioned earlier. Look at the number 0.200. After 0.200, there may be some zeros or non-zero digits. We are not sure about that. We are sure about only about 0.200. So there has 3 significant figures. They are 2, 0, 0. Zeros at the right of a number. That means right of decimal point. But if otherwise, if the terminal zeros are not significant, if there is no decimal point, for example, 100. Listen carefully. 100. 100. 100 has only one significant figure. 100 has only one significant figure, because there may be some addition, or there may be some existence of plus or minus 1 or plus or minus 2 errors. So 1 is a significant figure. Then second example, 100 point, that means 100 point, has 3 significant figures, because after point there may be some zeros or non-zero digits. We are not sure about that, but we are pretty much sure about those 3 digits, 1 and 2 zeros. After 2 zeros there exists a point, so those 3 figures are significant. The fourth example is 100.0, that means 100.0. After 0.0 there may be some numbers, we are not sure about that. So there 100.0 has 4 significant figures. They are 1, 0, 0 and the 0 coming after the decimal point. So this is all about the 4 points of analyzing the number of analyzing the number of significant figures. Next one, the addition and subtraction of significant figures. So how do we add or subtract 2 significant figures? The operation is carried out simply by adding the numbers, by placing the numbers below each number as the correct decimal places. So 12.11, 18.0, 1.012. Given below is the addition of 3 decimal numbers. So we are adding these 3 numbers and what we get is 31.122. The answer is 31.122. But remember, among these 3 values we have taken 18.0 is the greater value. 18.0 is the greater value. Here 18.0 has only 1 digit after the decimal point. 18.0 has only 1 digit after decimal point, and that is 0. And the result should be reported only up to 1 digit after the decimal point. So even though the answer obtained is 31.122, we need to take only 1 digit after 0, and that is 1. So the correct answer is 31.1, because we need to take only 1 decimal place after 0. Because why? 18.0 has only 1 digit after decimal point. I hope you understood. Multiplication and division of significant figures. So earlier we have learned about the addition and subtraction of significant figures. Here we are going to deal with the multiplication and division of significant figures. Given below is the multiplication of two decimal numbers, 2.5 and 1.25. Here we can see that among 2.5 and 1.25, 2.5 is a greater number. So here 2.5 has two significant figures, 2 and 5. So that the result must have two significant figures. While multiplying 2.5 with 1.25, what we get is 3.125. 3.125. But we have to take only two significant figures from the answer. So the result should be 3.1. The answer should be 3.1. It's all about addition, subtraction, multiplication, division of significant figures. Moving on to our last subtopic, that is dimensional analysis. Often while calculating, there is a need to convert units from one system to other. The method used to accomplish this is called factor label method or unit factor method or dimensional analysis. So in simple, what is mentioned here is while calculating a numerical problem, we know that there are some sort of units and measurements, but the final answer we obtained must tabulate the left hand side and right hand side of units. That is called dimensional analysis. So how do we carry out that? Let's find out. Example number 1. A piece of metal is 3 inches long. What is its length in centimeter? A piece of metal is 3 inches long. What is its length in centimeter? So here given the conversion, 1 inch is equal to 2.54 centimeter. 1 inch is equal to 2.54 centimeter. Now, even though the magnitude and the units are different, the overall values are the same. Now we are representing these two terms, the fraction. 1 inch divided by 2.54 centimeter, which is equal to 1, because both the numerator and denominator carries the same value. This is also equal to 2.54 centimeter divided by 1 inch. So 2.54 centimeter divided by 1 inch is also equal to 1. Here we are taking the second fraction, 2.54 centimeter divided by 1 inch. So 3 inch is equal to 3 into 2.54 centimeter divided by 1 inch. We are neglecting the denominator because of the number 1. Any number divided by 1 gives that number itself. So 3 into 2.54 centimeter. So finally we get the answer as 7.62 centimeter. Hence the answer. Example number 2. A jug contains 2 liters of milk. Calculate the volume of the milk in meter cube. A jug contains 2 liters of milk. Calculate the volume of the milk in meter cube. So, liter is a unit of volume. We know that the SI unit of volume is meter cube. So we have to convert 2 liter into SI unit of volume. So given here 1 liter is equal to 1000 centimeter cube, and also 1 meter is equal to 100 centimeter. So these are the two given terms or given two values. From these two values, we are applying the dimensional analysis to obtain the final answer. How do we do that? So, the second equation, 1 meter is equal to 100 centimeter. So, while discussing the previous case, here also we are writing the two terms as a fraction. 1 meter divided by 100 centimeter, which is equal to 1, and also it can be represented as 100 centimeter divided by 1 meter. Here we are taking the first fraction, 1 meter divided by 100 centimeter. We are taking the cube of the fraction. So 1 meter the whole cube divided by 100 centimeter the whole cube implies 1 meter cube divided by 10 raised to 6 centimeter cube. So how do we obtain 10 raised to 6 centimeter cube? 100 is equal to 10 raised to 2. So 10 raised to 2 the whole raised to 3. A raised to m the whole raised to n, which is equal to a raised to m into n. So 10 raised to 2 into 3, so 10 raised to 6 centimeter cube, which is equal to 1 cube. So cube of 1 is always 1. Therefore, 2 liters can be represented as 2 into 1000 centimeter cube. From the very first equation, 1 liter is equal to 1000 centimeter cube. So 2 liter is equal to 2 into 1000 centimeter cube. Next step, 2 into 1000 centimeter cube into 1. So any number multiplying by 1 doesn't change the value. Now 1 is also equal to 1 meter cube divided by 10 raised to 6 centimeter cube. We obtained that. So substituting here, the next step, 2 into 1000 centimeter cube into 1 meter cube divided by 10 raised to 6 centimeter cube. So multiplying, simplifying, we get the answer as 2 meter cube divided by 10 raised to 3. Now 1 by a raised to m is equal to a raised to minus m. Therefore, the answer can be rewritten as 2 into 10 raised to minus 3 meter cube. 2 into 10 raised to minus 3 meter cube. Hence the answer. The last example. How many seconds are there in 2 days? How many seconds are there in 2 days? So, as a common sense, we can directly calculate as 2 days equals 24 hours and 1 hour equals 60 minutes and 1 minute equals 60 seconds. So 2 into 24 into 60 into 60 can be written, but we should know how it obtained this kind of simplification. Let's find out. We know that 1 day equals 24 hours. So again we are writing the terms as a fraction, 1 day divided by 24 hours, which is equal to 1. It also applies to 24 hours divided by 1 day. It is also equal to 1. Similar is the case of 1 hour equals 60 minutes. So 1 hour divided by 60 minutes, which is equal to 60 minutes divided by 1 hour, which is equal to 1. Again we can write 1 minute equals 60 seconds. In that manner also you can write also that. How do we write that? 1 minute divided by 60 seconds, which is equal to 60 seconds divided by 1 minute, also equals to 1. Now therefore number of seconds equals 2 days into 24 hours divided by 1 day into 60 minutes divided by 1 hour into 60 seconds divided by 1 minute. So finally 2 into 24 into 60 into 60, and the answer should be written in seconds. So the answer is 1,72,800 seconds. Hence the answer. So this is all about this video. On next video we will be discussing about some interesting theories of chemical combination, then Dalton's atomic theory, and atomic and molecular masses. Thank you for watching this video. Have a great day.